Let's quickly do a couple more examples in a slightly different context of using differentials. So here we have position as a function of time, and let's say it's a somewhat similar graph. Let's say it's going, maybe it's sort of similar S-curve shape. And I'm not even going to really say what the position at t equals 3 is, because it's not really going to be important. The differentials style is particularly nice when we're really focusing on changes in variables and not so worried about what those variables are. And there's plenty of places where that's really the right focus. So let's suppose that, oh, actually, I think I chose 80 miles an hour in my notes. Okay. Let's suppose we have position s in miles as a function of time t in hours. So s is a function of t, and the velocity, well, that's the derivative of position, and we could write that as s prime of 3 equals 80 miles per hour. So once again, we're just getting a tangent line slope. All we know is that if we took the tangent line to this function, and one perspective here is erase the purple curve, erase s of t completely, and pretend that in fact what this, let's say a car, was doing on the highway was going through this this location at this time and going 80 miles an hour forever. That's what we're going to use to predict everything else about the motion. Now, as usual, as with the other video, we're not going to be able to accurately predict what happens significantly away from 3 hours because very likely that velocity is going to change. It's not really a straight line. But differentials are about what can we do by pretending the function is linear? And that's, again, differential calculus is all about that. Okay, so, for example, first example would be, suppose I just let the clock run 6 more minutes, or I have the change in time is 0.1 hours. How far does the car go? How far additionally from wherever the heck it was does it go? So we're going over a little bit, dt, and, well, I'll use red here, dt, and I'm going to not try to get the purple curve. I'm just going to say if this person kept driving at exactly the same speed forever, or at least for the next 0.1 hour, how far would they go? And that is a change in position, and that is a marker we're not going to use anymore. Let's say orange, okay? What is ds going to be? So stop for a second and forget you've heard anything about calculus ever and see if you can answer this question, because this is not really fundamentally calculus anymore. Calculus really exists to get away from these sophisticated ideas and replace them with good old-fashioned multiplication, division, direct proportionality kind of arguments. Okay, well, and that's exactly what this notation, I hope, makes clear. ds over dt is the rise over run for that red line. We know that that is 80 miles per hour. Let me leave the unit in this time. So ds, very like what we had before, 80 miles per hour times the known change, 0.1 hours, and we get 8 miles. It's just distance equals rate times time. That's all it is. And the reason we can reduce it to distance equals rate times time is this crucial step of going away from the complicated function, replacing it with its own tangent line. Now, how do we get this in the first place? That's where the calculus really comes in. That's where the new ideas and the new manipulations and techniques come in. What are various ways we could take like a formula for this function or other data about this function and get this 80 miles per hour? Once you've got it, and once you're willing to make this bargain that we're okay with this approximation, the straight line approximation, it's back to d equals rt, basically. So I'm not saying that there's nothing new on calculus, but once you set this kind of equation up, once you have this data, don't overcomplicate it at that point. And differentials provide a very nice terminology to do that. Okay, so in 80, if you're going 80 miles an hour and you went a tenth of an hour, duh, we go 8 miles. And we could flip it. We could say how far, how long will it take to go an additional from wherever we are, let's say 4 miles. Very easy if you build on the last question, but let's suppose we hadn't done that, and then we can use that as a check. ds dt equals 80. It doesn't look like an 8. Okay, now it's the ds that we know, very similar to what we were doing in the last video. 4 miles. Let's put in the units. Ooh, we can cancel miles. Okay. And then we can multiply by dt. 4 equals 80 times 1/hour times dt. Divide by 80 and multiply by hours, and you get 4/80, or 1/20 hours is the time, or 3 minutes. Okay, surprise, surprise, especially having done the previous example, if you want to know how long it's going to take to go an additional 4 miles at 80 miles an hour, it's going to take 1/20 of an hour, or 3 minutes. I hope that most of what you've seen in the last 5 minutes and 30 seconds has been rather underwhelming. It's not supposed to be complicated. Once again, once you get this information and you want to do these approximations, it should be very simple math. Remember though, it's an approximation. There's the terminology for that. Instead of looking for delta S, the actual change in position, how far you really go, we're settling for something rather different, which is ds. And more advanced stuff in calculus talks a little bit more about how can you talk about how different are those and how can you get better approximations. But this is the heart of it, to settle for the linear approximation.